So now let's take a look at our mean, variance, and standard deviation for a binomial distribution. Specifically for a binomial variable, we can find the mean, the variance, and the standard deviation just by knowing the values for n and p. I realize that the variance and standard deviation require knowing q, but q is equal to 1 minus p. So we only need to know n times p. These are great formulas to know, so you'll want to make sure that they're easily found, highlight them, circle them in your notes so that you know where they are. Let's use these formulas to find the mean, variance, and standard deviation for the distribution of correct answers on our quiz. Recall from our quiz that n was 5, p was 0.25, 1/4, q would be 0.75. Then if we wanted to find our mean, n times p would be 5 times 0.25, which would give us 1.25. Generally, we round one more place than x, so we would round that to 1.3. To find our standard deviation, n times p times q, 5 times 0.25 times 0.75 will give us 5 times 0.25 times 0.75 will give us 0.9375, which we would round to 0.9. And this 1.3, sorry to jump back, the mean would be 1.3 questions correct. 0.9 is square questions, which makes no sense. And then for standard deviation, we would take the square root, and we take the square root of 0.9375. We've already calculated it in our calculator, so we take the square root, and we get 0.968, which we would round to 1.0 questions. Okay, I do want to do one thing really quickly. I know these formulas hit really fast for us. Here is our technology from before. So I'm in Excel. I might have my probability distribution table for my quiz. I have n and p here. And we can use the formula to very quickly calculate mean, variance, and for q, I'm going to do 1 minus p, and our standard deviation. We get the same values. But what I do want to show you is that this idea of mean is exactly the same as the way we did calculate it. Just because we're talking about a binomial distribution, we have this special formula that comes up that makes what we were doing before equivalent to n times p. The way to calculate the mean for any discrete probability distribution is to add up x times p of x. So we would add up x times p of x, x times p of x, all the way down, and hit enter, and we get the same formula. I could do one more step and calculate that variance. For the sake of time, I'm going to leave that. If you want to try it on your own, try it. It's a good way to remember how to do general variance for discrete probability distributions, and it also allows you to see that this simplified formula is the same as what we were doing before. It's just because we have this different structure, this very specifically set up structure for binomial distributions, how these procedures reduce into these very simple formulas. So let's go back and work some more problems. Example 5 for doctor visit surveys. A survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. Okay, so working this problem, we need to identify some pieces. I have a lot of information here, and it's not labeled as clearly as we may want it, so we need to try to interpret it. A survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. This first sentence is an empirical probability. 1 out of 5 Americans, this is our p, 1/5 or 0.2. Now, if we get more specific, if 10 people are selected at random, Find the probability that exactly 3 will have visited a doctor last month. 10 people total, that's n. Exactly 3, that's x. So right now we're not using the mean, the variance, and the standard deviation. We're just going to calculate a binomial probability. So we have our n, our p, and our x, and we're looking at exactly 3, so x equals 3. We can either do this by hand, or we can plug it into technology. Doing by hand, n factorial over n minus x factorial times p to the x power times q to the n minus x power, and I'm going to replace my p and my q here. P is 0.2, q is 0.8. Simplifying this out, 10, 9, 8, 7 factorial. 7 factorial will cancel with 7 factorial. 3 factorial is really 3 times 2 times 1. I can cross out 1, 3, I can cancel the 2, and I get 5 times 8 is 40. 40 times 3 is 120, so that whole combination should be 120 times 0.2 to the third times 0.8 to the seventh. And we can pull up our calculator. 120 times 0.2 to the third times 0.8 to the seventh equals 0.2013. So the probability that exactly 3 have visited a doctor last month would be about 20%. Let's see if we can recreate this in Excel. So for x equals 3, binomial distribution, 3, 10, 0.2, and false, 0.2013. We have a match. Okay, to contrast this with at least 3, let's take a look at example 6. A survey from Teenage Research Unlimited found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. We'll do some work by hand, but we're going to do the calculations using technology. So let's write down what we know. Our probability P is this 30%, this empirical probability here, 0.3. 5 teenagers are selected at random, and at least 3 of them will have part-time jobs. So the bigger number is always n. N is 5. And for at least 3, this means x is greater than or equal to 3. X is 3, 4, or 5. We want to look at all 3 of these. We've got P, N, and X, and for X we're looking at 3 different values. So let's take a look at it in Excel. And for this one, I want us to calculate it with the formula, but I also want us to look at it graphically so that we can start to get used to seeing what's going on in our problem, as well as using the table. So let's first just calculate. N is 5, P is 0.3. We need to do the probability x is greater than or equal to 3. X is at least 3. So we can do a binom.dist. Now, cumulative means 3 or below. We're not doing 3 or below, we're doing 3 or above. So I want to make sure that we're aware of that. At least 3 means 3 or greater. The cumulative here means below, not above. This distinction will become very important when we move into Chapter 6 as well. The same thing's going to happen to us in those formulas. So cumulative is below, we're doing above, so we cannot use the cumulative being true. We have to use false. So binom.dist, we've got 3, n, p, false, but I'm going to add to that another one, binom.dist, 4, n, p, false, and one more, 5, n, p, false. This is one way to approach the problem. So the probability that at least 3 of them will have part-time jobs is 0.163. If I wanted to make a table, 0 through 5. Our probability here is different than our quiz probability, so our numbers are going to be different for the probabilities. They'll be close because 0.3 is close to 0.25, but they will be different. So here, if we create the table, we can use cell references and then drag the formula down. I'm going to go ahead and lock my N and my P so that I can just directly go ahead and drag it down. And there we have it. X is greater than or equal to 3 means we're adding up 3, 4, and 5. So if we try to add up 3, 4, and 5, let's do it. Sum 3, 4, 5, we get the same value. That's important. The other thing that we could do, we want 3. So we don't want 0, 1, and 2. We can use this idea of complements. I can say 1 minus the probabilities of 0, 1, and 2, and I'll get the same value. So 1 minus sum 0, 1, and 2. I want to subtract those off and keep 3, 4, and 5. And if I do that, I get the same value. And I'm going to do one more thing because I think this is important, especially for us as we move on and we're not using the tables necessarily, we're just using the formulas. 1 minus binom.dist, do 2 NP, and this time we're going to do true. We want to add up 0, 1, and 2 and then subtract them off. We get the same value. So there are multiple ways to look at these problems and get the answers. Find a way that works for you. If you want to do each value individually and add them up, in a lot of cases that will work, but if our N is big, we may not want to do that. That might take too long. And making a table might take too long. So we just need to be aware of the different ways that we can calculate probabilities when we're talking about more than one thing, more than one trial happening. Add them up individually, create a table and add them up, do 1 minus what we're not adding up when we create the table, or do 1 minus a cumulative if we're doing greater than or equal to. If we were looking for something, a probability less than, so at most 3, we would just say binom.dist 3 NP and then true. So the at most or 3 or less, those will be true cumulative probabilities. We'll do an example of that a little bit later. So we found that probability of at least 3 having part-time jobs as 0.163.